Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we have, in this session, we've got 3 talks. 2 of them are really in the what we call our applications track. The 3rd talk that was originally scheduled was canceled, but we were fortunate enough that we've got a really great replacement, and that is will be the 3rd talk, and I'll introduce it when the time comes up. But right now, I would like to introduce Magdalena Balazinska, and from the University of Washington, and she's going to be talking about interactive fault-tolerant data analytics in the cloud. So Magdalena.
Thank you. Thanks everyone for coming. Before actually I start, I just want to say that this project is part of a larger project in the computer science department that we call Nuage, which is the French word for cloud. The motivation for the Nuage project is pretty much Ed's talk this morning, so I don't have to repeat it. But we're looking at it from a database perspective. We are database expert, and we're asking the question, people in sciences especially, but also in other domains, have lots of data that they need to process, analyze. Where are current tools failing? And should we be building new tools? How can we improve existing tools? How can we help people get onto the cloud? So this is kind of the high-level motivation for our project. This project is, of course, based on hard work by the following great graduate student. And in particular, today's talk will focus on Prasang's work, also in collaboration with Young Chul. We also have several great faculty, and this is actually an interdisciplinary team. We have partners also in astronomy, and Bill Howe, who's a computer scientist, but also has strong ties with oceanography and other sciences. So on this kind of general Nuage project, we have several goals. Overall, we want to help people, in particular scientists, with their data management problems. For this, we have projects that look at just simplifying data management. How can we help people get over the hurdle of actually accessing cloud-based systems? How can we help them just write simple queries to access a database? If they go to the next step, how can we help people express complex analytics in systems such as MapReduce or parallel databases in a way that results in an efficient execution? And finally, which is the focus of today's talk, how can we help people when they do this type of large-scale analysis using MapReduce parallel databases? How can we help them get more interactivity and also kind of still preserve kind of large-scale scalability and resilience? And for this, we have tools that allow people to just observe what is going on. For example, do time-oriented progress estimation. But also, this is kind of really the focus of today's talk, is how can you get both interactivity, pipelining, and fault tolerance together. But I'm mentioning this quickly because if you're, this is the beginning of the workshop. If you'd like to talk about any of these other topics, I'd be happy to talk about this offline. So what is the problem? The problem is the following. I have some sort of large-scale data analysis that I would like to run using maybe MapReduce, using maybe a parallel database, but I would like to see results incrementally. I would like to see results directly as they can be produced early on during the execution of this long analysis, because I would like to have early insights, perhaps to cancel the job if the results are not what I expect them to be. At the same time, I would like to make sure that the entire computation terminates and finishes quickly. And you might ask, well, why is this a problem? This is difficult because it's actually difficult to have both requirements at the same time. Typically, if I would like to see results incrementally, I want to just pipeline data through all my operators. But if I do this and a failure occurs somewhere in my query plan, I will have to restart the query, so that kind of my total time to completion is going to be longer. So let me illustrate by showing what today's tools are actually doing. So first, what I could do is I could use MapReduce. And MapReduce takes the approach of fault tolerance, but without interactivity. So in this case, as you all know, in a MapReduce system, my data is going to start on disk. And to run my analysis, I'm going to first read the data from disk, have it processed by a set of map tasks that are going to then write their intermediate data to disk. Then I will have a second step, which is the reduce step, where all the reduced tasks are going to read the data from disk, process it, write it again to disk, and I can kind of continue by having additional MapReduce jobs follow on with subsequent computations. At large scale, when failures occur, this is great. Because if anything fails, like if this map task fails, all I have to do is just reprocess the data, regenerate the intermediate results, and I'm done. The problem, though, is I see nothing. I don't see any results until all the data has been processed because I have this blocking mode of processing. Alternatively, what I could use is a parallel database. And here the strategy is different. The strategy is to read the data from disk and stream it through all the different operators in my query plan to produce results. If my operators allow me to see results incrementally, if those are non-blocking operators, then I can get early results as basically the first tuples are getting processed. So this is great to have incremental processing to see early results. But if something crashes, well, I don't really have a choice. I have to restart my query, which is not good if I'm going to really try to scale it. So the question that we asked in this project is, can we do better than these two extremes? And the answer is, of course, yes. And the first part of the solution is that actually nothing prevents me from taking a pipelined query plan and making it fault tolerant. In fact, I can do this using existing techniques from the literature. But the second question we started to ask is, well, which strategy should we be using? And actually what we concluded, and this is really our contribution, is when I have this large-scale query plan, I can actually mix and match and decide to perhaps have no fault tolerance in one fragment of the query plan, make some other parts fault tolerant, and kind of do this mixing and matching that will allow me to get the fastest expected overall completion time. As an example, if I have a query plan with, let's say, a very simple stateless operator, perhaps it's not worth to do much, because if this operator crashes, I can just kind of keep going where I left off. Whereas if I have a very complex aggregate operation with lots of state, well, then perhaps this is an operator that I would like to checkpoint. So what we wanted to do in this project is to enable kind of this use of these different strategies inside a single query plan and have an automated way to figure out which strategies to use. So how can we accomplish this? Well, the first part is that I would like to take a query plan and have this ability to mix and match the different strategies, fault-tolerant strategies. So here's an example of a very simple query plan with only 3 operators, O1, O2, O3. What I would like is for each of those operators to be able to autonomously decide what fault-tolerant strategy to use, perhaps using no strategy at all. But if something crashes, I would like to restart these operators individually. I don't want to have to restart the whole query plan. So for this, we came up with a protocol that's actually very simple and uses pretty known techniques from homogeneous fault tolerance strategies. So the first rule in our protocol is that all the tuples that are going to be transmitted from one operator to the next must have unique identifiers. This will allow us to kind of keep track of the progress of different operators. Second, if an operator crashes, it's actually allowed to ask its upstream neighbor, the upstream operator. So if O2 crashes, it's allowed to ask O1 to resend any subset of the data that it produced earlier. So this is, for example, in MapReduce, this would be easy to satisfy because O1 would write its data to disk. So if O2 asks for any subset of it, it can just read it from disk and resend it. If I don't have any fault-tolerant strategies, maybe this will be more difficult to satisfy, but maybe still possible. Here we don't ask how, we just require that the operator be able to do this. For efficiency, in many cases we can actually have some guarantees that an operator, once it made sufficient progress, even if it crashes, it won't ask for a certain subset of tuples. So we add this third rule that an operator can optionally acknowledge the data that it received. And if it does so, it guarantees that it's never going to ask for that data again. And that can allow the upstream operator to optimize what it's going to do. And finally, we also ask each operator to remember the last input data item that it received, such that if something crashes, restarts, it can basically ask its downstream neighbors exactly where it crashed, where it left off, and where to continue processing from to avoid any duplication. So these are very simple 4 rules. And as you notice that if now each operator can implement any fault-tolerant strategy that it wants, including doing nothing, as long as it can guarantee that it can satisfy these 4 rules. So how would failure recovery works? Well, if an operator, let's say O2 crashes and restarts, what it can do after restarting is it can ask all the downstream neighbors for the last tuple they received, so it knows exactly where it left off. Optionally, if O2 saved any state, it can recover that state. It doesn't have to. It can definitely ask O1 to resend any subset of the data. And with this, it can simply continue processing, reprocess it, and wait until it reaches the point where it left off, and it can continue sending data without duplication to its downstream neighbor. So as you can see now behind this protocol, I can implement different strategies. For example, if O2 is a stateless filter operator, perhaps I don't need to do anything for fault tolerance. If the operator crashes, it simply asks its downstream neighbor where it left off, doesn't need any state, and it can ask its upstream parent to keep sending data exactly from the corresponding point where it left off, and we can get something very efficient. In contrast, if, for example, O2 is some join operator that accumulates lots of state, if that operator chose to do nothing and it crashes, it would have to restart and reprocess all the data from the beginning. In contrast, if that O2 operator chose to checkpoint its state, then it can recover that state from disk and only continue processing data from that last checkpoint. So this allows us to kind of do this mixing and matching. And the strategies that we do investigate in our prototype include the strategy of doing nothing, which I described with the example of the filter, the strategy of checkpointing the state, which I just described with the example of the join, and also the strategy of materializing, which is what MapReduce does, where here each operator simply writes its own output to disk. Doing this doesn't help the operator recover itself, but it helps when the downstream operator crashes and asks for previous data. But now the big question is that, okay, this is great. This all works. I have to be a little bit careful how I implement these strategies to get efficiency. But now the question is, well, how do I choose which strategy to use? If I use something like checkpointing, I will have maybe higher overhead, potentially faster recovery. If I do nothing, I will have lower overhead, but potentially slower recovery. How can I figure out which strategy to use? So for this, we developed what we call FT-opt, which is a fault tolerance optimizer. The input of this optimizer is the query plan and also information about the cluster, such as the amount of resources in the cluster and the probability with which different nodes can fail in the cluster. The output of the optimizer is the strategy for each operator in the query plan. If an operator is going to checkpoint its state, we also compute the checkpoint frequency for that operator. And optionally, we can have a resource allocation, because depending on how many resources I allocate to different operators, then they have more slack or more room to do extra fault tolerance. So how does the optimizer do this? How does it produce its output from this input? So for this, it actually selects the fault tolerance strategies, resource allocation, and also checkpoint frequencies that minimize the following objective functions. So here I didn't want to give the formula because the intuition is pretty simple. What we want is minimize the total runtime for the query. So we work with query plans in the form of a tree, and we look at the longest, the slowest path in this tree, and we look at the time to propagate the first tuple or data item all the way to the last operator, and then the time for the last operator to actually complete its processing, plus any time that we're going to spend recovering from failures. Of course, this is subject to constraints on data rates. Consecutive operators need to have matching data rates. Constraints on resource capacity, etc. And just for those interested, we use geometric programming. So one component that is actually difficult to make this happen is that in order to compute this function, I need to model how the operators work. And that means every time I come up with a new operator, I have to have new models of how fast they're going to process their data, how they're going to behave in different failure scenarios with their different fault tolerance strategies. So for this, we actually developed a technique that allows us to, we only ask an operator writer to basically specify two functions. One that is the time it takes to produce an output tuple, assuming all the data is in memory. And the other function is simply a mapping of how many output tuples this operator produces, given a certain number of input tuples that it received. And what we do is we actually compose these functions together to figure out that in this setting, the operator will be limited by the input rate, for example, or is going to be limited by its CPU, and how the output is going to look like. So the approach that results is that it's pretty extensible. It's not too difficult to add new operators. The optimization technique that we use is currently pretty straightforward. We simply enumerate all the given a query plan. Our optimizer uses a brute force approach, just enumerates all the fault tolerance configurations. For each one, it finds the resource allocation, the checkpoint frequencies that minimize this objective function, and then it picks the plan with the lowest expected total runtime. So of course, the question now is, does this work? Well, let me show you some graphs. So the first question is, of course, can our optimizer actually predict how long the different operators are going to perform their processing? So this is an example configuration that is pretty representative of the kind of predictions that we make. This was a query plan with 4 operators, select followed by 3 joins, and we used the 16 machine cluster. On the x-axis here, we have different strategies. So either the operators do nothing for fault tolerance, all of them materialize their output, all of them checkpoint their states. Here we had 10 checkpoints for each operator. Or we use a hybrid strategy, which was the strategy selected by our optimizer. In this case, it was for the first operator to materialize, the other 2 to checkpoint, and the last one to do nothing. And as you can see, we're not perfect, but we do kind of nicely follow the trend. And this is actually to have very accurate estimates can be difficult. One thing that we actually do right now to simplify the problem of this accurate estimation is that we, on those 60 machines, we actually have 32 disks, and we ensure that each operator partition uses its own disk for writing its checkpoints, writing its data, so we don't have to worry about sequential versus random I/O because each operator gets sequential I/O. That really simplifies our model. It could be extended for more complex scenarios, but this is kind of one of the challenges to get these types of reasonably accurate estimations. So the second question is, okay, given that we can predict the runtimes with some reasonably good accuracy, well, does fault tolerance optimization matter? Does it matter that we do what we do for fault tolerance? So this is actually another example of a configuration. It's exactly the same query plan. We slightly tweaked the data rates here so that materialization was not as on the previous graph, it was basically really losing compared to the other ones. Here it's a little bit better. And what you can see is several things actually interesting in this graph. So here we have the different strategies, starting with what MapReduce would do, which is to kind of write data out and materialize and block. What the parallel database would do, which is just blindingly fast process the data, but if something crashes, restart the query. The other ones are uniform strategies of all operators do nothing, checkpoint reasonably frequently, checkpoint infrequently, materialize their data, or the hybrid, in which case the hybrid selected by our optimizer was to, as I mentioned, materialize, checkpoint, and do nothing. And there are several interesting things. On the y-axis, we have the runtime for this query. The blue one is the normal runtime without the failure, and the red one is kind of the expected time to recover from one failure that happened sometime during the execution. So in this specific configuration, MapReduce was really not the optimal strategy because the materialization was just adding a huge overhead to the runtime. But as you can see, recovery from failures was much faster. And what is interesting is several things. First of all, if we take kind of these techniques of materializing everywhere or doing nothing, but we at the same time materialize everywhere but pipeline data through the operators, or do nothing but make the operators individually recoverable, we get into these 2 strategies, which already help us improve the total runtime. The second strategy that we can see is that our optimizer may not necessarily pick the best time. Here, doing nothing in this configuration is a tiny bit faster in the end, but still we can avoid any bad plans. So we are pretty good at selecting good plans, even if we don't necessarily select the perfect plan, because our estimates are not completely accurate. So in summary, we are finding in our experiments that in different settings, different strategies can be preferred, and that we are able to find a good strategy, often a hybrid one, automatically. The savings can be significant. We are seeing 30-40% improvements, but that does depend on the configuration. The challenge is that the models do need to be accurate, and this is difficult in certain scheduling and in certain settings. In our case, like I said, for example, we ensure that each operator writes to its own disk to make sure we can predict the times more accurately. And overall, as Ed said really well this morning, we have a data deluge. People have lots of data. They need help analyzing, processing this data. I just described one example of a project that we're doing to help them with this. But this is part of our broader Nuage project, and I invite you to visit our website at nuage.cs.washington.edu. And finally, none of this would be possible without great sponsors, including Microsoft. Thank you.
Okay. Yeah, I was expecting a mic.
Oh.
We don't need it.
No, I think I can.
Yeah.
Okay. If I may, I would like to formulate two questions, but if there's not enough time to answer both, perhaps we can take one at a time. So the first is, well, Amazon EC2 had less than 20 hours of downtime for a whole year, so 2009. What were the availability or failure rates for the resources that you've assumed in your experimental setup? That's the first question. And the second is, I've heard that you're trying to optimize makespan. My question is whether makespan really has an impact on the interactivity of the applications, and why didn't you look also at costs? Or if you looked, maybe... Okay, so these are the two questions.
So let me maybe answer the second one first, because I think it's a bit more interesting. So the question is that here in our optimizer, we optimize for total runtime versus perhaps we would like to optimize some other metrics, and does total runtime help with interactivity? So I don't know if that's exactly...
Yeah, it's partially... Well, depends a bit what kind of interactivity. If you want partial results so that you can progress in your own work, then it doesn't. If you want the complete set of results by the time you want to look at them, then that's the makespan, and then it helps.
That's right. So what we are doing is with our fault-tolerant strategies in our protocol, you do get partial results. You do get results incrementally. But within this context of having this ability to get results incrementally, we minimize the time to get all the results. And you could change the optimization metric to be something else. This is kind of the one we chose to explore because it kind of gives you the best of both worlds. You want to have the ability to get results incrementally, but within this you don't want to sacrifice the total runtime, because if you would sacrifice the total runtime, you could just pipeline everything, and if something crashes, just restart the whole query. So this way we kind of have benefits from doing this partial materialization. And it would be possible to explore other for example, other optimization functions such as cost, which simply we didn't look at that yet.
But then the exploration space grows exponentially with each axis that you're adding. If you're adding also intermediary results, then you're looking at something else. If you're adding costs, the same.
That's right. And then the problem is more interesting. So currently we explore very naively. So our goal was to simply say, is there a point in doing this fault-tolerant optimization? Do we gain anything from it? What do we gain? And that's the question we were trying to answer. And once you go past this, then of course, yes, you would have to be smarter about the way we explore the space, not explore the entire space in this brute force manner, etc. So I don't know if maybe someone else.
Did you consider changing the granularity of your operators?
Changing the granularity, do you mean having just more operators or more partitions of the same operator?
As you're stepping through, you're basically building in optimizations for fault tolerance within each block, within each operator, right? Mm-hmm. And the MapReduce framework provides sort of a natural fault tolerance for failure between nodes and so forth.
Yes.
And I guess the question is you're doing it sort of within the operator, you're providing fault tolerance. But if you were to split that operator into, say, more operators, you're basically end up making there's more individual steps in your operation, but you're relying more on the framework and less on custom code or custom handling. Look at that at all.
So the question is whether we would, so if I take an operator that is a black box operator, I could partition it into 3 operators or group these 3 operators into 1 operator. What our framework would do is make that whatever granularity we choose individually recoverable. So this is similar to MapReduce, that whatever is your operator becomes the unit with which you can recover from a failure. The advantage of grouping many operators together is you can kind of send the data really fast from one operator to the next because they're grouped together, perhaps running in a single process. The advantage of splitting them up would be that if those are kind of multiple pieces of a very long computation, you could recover even throughout that computation. So I guess this will be a trade-off in how you can recover.
To a degree, you're reinventing a framework, right? And the question is, at what point does it make sense to bundle for the sake of performance versus to segregate because I have less complexity in my operation, I have less pieces of additional code to my library.
That's right. So I guess the way this bundling comes up in our scenario is that if it makes sense to bundle some operators, we will likely find that it's probably worth it to do nothing to recover a bunch of these operators, except maybe at the boundary. And that might be a hint that these operators could benefit from being combined together. This is the way it would, I guess, be reflected in our framework. But we don't offer this as an option. We didn't explore this as an option.
I have one question myself. So one of the things about failures is you scale up systems to very large scale. Failures are roughly continuous, whereas the comment was made that Amazon looks like it's up all the time. It's really in a constant state of failure. Every large-scale system is. And so, but your experiments look like you looked at sort of one failure. Have you thought about the scalability or the adaptability over sort of as you get larger and expecting a greater density of failures?
That's right, and our framework can handle this. So the greater the density, it basically takes kind of the probability of failure per node, per time unit, if you want, as an input. So if the failures are very likely, it's going to favor techniques that do more fault tolerance, because then I want the granularity of my recovery to be smaller. So we do take that as a parameter. In the experiments, it's just that it's kind of easier to show this is the expected time, the total runtime, and then the added time for each recovery. So if you fail multiple times, you would add these red blocks on top. And eventually, depending on how many failures occur, the strategies that have smaller recovery times would then start to win. And we take that as a parameter, clearly. That's why, and it has to be an input because it depends on the network properties.
Exactly. I think at this point maybe we should move on. Thank Magdalena again. We have the next talk. So our next talk is by Paul Watson from the School of Computing Science at Newcastle. Paul has been working on some really interesting problems using cloud infrastructure for some time. He's a real pioneer in this, in the application space, and he has been doing some very impressive stuff with pharmaceutical and chemical related things, and we'll let Paul tell us more about that.
Okay, thanks. So I'm going to talk about some work that as Dennis was saying, we've been doing with some cancer research scientists at the National Institute of Cancer Research at Newcastle. And when we talked to them about what they were trying to do, it came down to these two questions that were really important to them. So they do experiments, generate molecules, and they want to know what are the properties of this molecule. Or they want to turn that question around and they want to say, well, in order to develop a drug, we need a molecule with a particular set of properties, and how can we do that? And the traditional answer is that, well, you go into the lab and you get the test tubes out and you start to do the analysis. But of course, there's a lot of issues with this. It takes quite a bit of time, particularly if you've generated a large number of molecules as a result of your experiments. There's a high cost in doing this. And of course, there are often ethical issues because for things like toxicity, you often have to do animal experiments in order to determine the results. So the team we're working with have been looking at alternatives, and the main one is something called QSAR, so quantitative structure activity relationships. So the idea here is that you go and you gather as much information as you can about molecules that are in the literature or in databases, where for the molecules you know what the particular activity you're interested in is. So you look at a paper and it says for this molecule the toxicity is such and such. And you gather all this information together for the activities that you're interested in, and then you're trying to generate these functions which allow you to predict, based on the structural properties of those molecules, if you come across a new molecule you've not seen before, what those properties will actually be. So that's the idea. So then, rather than do the experiments, you use these functions that you've generated in order to do the prediction. This allows you to rule out lots of molecules that you've generated which won't have the properties you're interested in. Just focus on 10, a dozen that look particularly promising, and then you actually go ahead with the experiments on those just to validate that the predictions are true. And it's quite interesting the way in which people generate these models. So one of the things that I've noticed in computing for a while is that some people have favourite ways of generating models, and it seems quite often they pick one when they were doing their PhD and they stick with it through thick and thin, right through their whole career until they retire. And the chemists, of course, aren't particularly dogmatic about the models. They just want to get on with the chemistry. And so they were fed up with people coming along and saying, oh, you need to try our model building technique. It's much better than the ones that you've already used. So they developed this thing called the discovery bus. And the idea of this discovery bus is a general purpose way of building models competitively. So what they do is they've got a database of all the data that they've collected from publications or from databases. They've got existing model building tools, and there's a whole set of them. I'll mention some of them later, but things like linear regression, neural networks, decision trees, and so on. And when they get some new data, they feed it into this system, and it combines it with the existing data. Then it tries all of these different model generating techniques one at a time at the moment, and then it compares the results, and it just picks the one which produces the best results. So they don't care which one it is. And if you come along, this is why I've also put model builders here as an input. If you come along to them and say, I've got this new technique, they'll say, great, we'll put it into our system and we'll just try it. We'll see whether it's actually really better than the existing techniques. And if it is, you get better models out of it. If it isn't, then you just discard the results. And then we've got the scientists who just want to be able to predict the properties of molecules. So they're at the top there in this diagram. And they're just going to a website. So this website that David Leahy, who came up with the Discovery Bus, his team produced it. They're building up, and they're putting all of the results into this website that they generate. So chemists anywhere could then go and predict the properties of molecules. And if you go a level below this to have a look at what's going on. So I'll put this up here because later on I want to talk about how we might get some scalability through the cloud with this Discovery Bus system. Then you can see at various stages. So you do the typical thing where you take the data for a particular activity, you split it up into a training set and a test set. For the training set, you work out the particular descriptors that you're going to use for prediction. So this could be the solubility, could be the number of atoms, something as simple as that. Could be something to do with the shape of these molecules. And then you combine these descriptors in particular ways, and then they have to filter out descriptors because you want to try and reduce the number of descriptors you're using because for one reason, the more descriptors, the longer it takes to do the learning. But the second reason is that if you can use fewer descriptors, then you often get more generalizable results. So the results that you get aren't so specifically tailored to the data that you train it on. They generalize against new molecules that aren't in the training set. So they do that. And then they fire it off, as I say, to all of these different sorts of models. So there's 4 shown there, but there's a few more that they use in the system as well. And then they compare the results and pick the best ones and put those into the website so that scientists can then use them. So that's the basic structure of the Discovery Bus. And this was all going very well until. There's been so we've heard about, in Ed's excellent talk, we've heard about this data deluge in many areas of science. And it turns out that in chemistry as well, there's been this deluge of new data. So they can now go and pick from these data sets. So you can see the top one, Kemble, data on 600,000 different compounds. And that's been gleaned from scientific publications, going through things like Wombat, where for Wombat PK, where they're basing the activities that they put in the database on clinical measurements. And so for all of these data sets, it says, so here's the molecule, here's some structural information about it, and this is the activity. So that's the raw material that they use to feed into the Discovery Bus. But the great thing about this, so the great thing is that you can then, as you get more data, you can generate more models, and you can generate better models because you can produce a better fit for the models you're producing. But in the end, the amount of data has killed off their existing system because when they got access to these amounts of data, they did some back-of-the-beamat calculations, and with their existing system, it was going to take them 5 years to drive this data through the system and produce better models. And of course, by the time the 5 years was up, there'd be more data and so on, so they'd never ever be able to catch up. So this was the challenge that we've been working on, helped by Microsoft, to see whether we could actually use cloud computing to get this down to a reasonable amount of time. So this is what was for reasons lost in the mist of time, called Project Junior, which Microsoft have kind of been funding for about 18 months now. And so the idea was to use Azure to try and get this down to weeks rather than years, and to make the data available through the website. You can see the website over there. So trying to speed this up. So if you look at the possibilities for doing that, well, for each different activity you have data for, you can process that information in parallel. So that's one level. But also within this workflow, you've got these opportunities, and some of them are obvious. So you'll have guessed that you could have tried all these different model building techniques individually. That's easy. As it turns out, you can also calculate different descriptors in parallel from the data that you have. And the business about filtering the descriptors, as I say, to try and reduce them to allow the results to be more generalizable, then you can also, there's opportunities for parallelism in there as well. So this is what we were trying to do. So the approach we took was the discovery bus is quite a complex bit of software. The main person who wrote it about 10 years ago is no longer available to help us do this. I guess that's something that's quite common with all of these old codes. So what we decided to do was, rather than throw it all away and try to re-implement it, what we would do would be to try and take the existing discovery bus, just capture it as a set of VMs on Amazon just to give us some stability, and then to focus on those bits where we thought we could parallelize it. And for those parts, we would then send those parts off to Azure. And in order to do this, we used a solution called eSign Central that we based most of our work on. So a slight divergence from the discovery bus. I'm going to talk a little bit about eSign Central so you understand how we're actually driving the Azure cloud. So one of the things that has always slightly worried me about whenever there's a new wave of computing comes along, so we heard it with grids and now with clouds, that some people give the impression that because they've written the Hello World program and it turns out to be quite easy, then all of the problems of building scalable, dependable, distributed systems all magically disappear. Whereas actually they don't, they just move. And in fact, the first talk in this session was an excellent example of that, taking existing techniques from databases and moving them into cloud computing to solve those problems. And so what we decided to do was to see, well, rather than have people build from scratch their applications on cloud. So Ed in his talk talked about the fact that he said something like Amazon was the cloud for developers because you could build everything right from scratch. Well, you can do that, but you need very good skills if you're to really build scalable distributed systems on that sort of low level. So we were trying to think about how we might make this easier. So if you look at this diagram on the left, I guess this is the consequence if you just built on a low-level cloud infrastructure. So you say to your database, your designers, your developers, there you go. You can have as many CPUs as you want. You can grab all the data storage you want. Just get on with it and build your applications. And you end up with them building from quite a low level and building. The danger is every scientific application that they build is a silo. It's all built in a bespoke way. There's no sort of commonality in the way it deals with security or scalability or how you run tasks and so on. And you've got your users at the top using these applications, which probably all have different sorts of interfaces and don't interoperate. So we decided to try an alternative approach where, I've been running this eScience Centre at Newcastle since 2001. So after about 6 or 7 years of developing software for about a dozen different sorts of scientists, we sat back and thought, well, what are the common things that you might want in a science platform for the cloud? What is it that's common across these projects? So we started to think about building that sort of system. So the idea is that you've got your cloud at the bottom, but you've got this cloud science middleware, if you like to think of it like that sits above it. And so you've just got thin, hopefully relatively easy to write science applications that sit on top of that. And so we rejected the one on the left and set off for the one on the right. And so the idea is that we've got this science cloud platform for developers, and at the top, we decided to take a software as a service approach for users. So everything through a web browser was our mantra in designing this. And when we'd looked at all of these different projects, the 4 things that people seemed to want to do was, so it's this data deluge that's the issue, and everybody wants to store the data, they want to analyze it in some way. Eventually, they want to automate that analysis when they're happy that there's a common way to do something and they want to share best practice. They just want to capture that and allow you to redo the analysis at a press of a button. And finally, they want to have some way to share their data in a controlled way, not make it all publicly available instantly, but do it with their PhD students and their collaborators. And perhaps eventually, when they've got the paper in Nature or Science, they might then make it available to the public. So we designed this platform which tries to capture these things that we thought were important. So at the bottom, you've got the raw cloud infrastructure with the processing and the storage. And in the middle, we've got workflow enactment, which seems to be a good way in eScience for people to actually automate analysis. We've got ways for people to upload services and run them in the cloud. We've got social networking as a basis for collaboration, building communities and sharing. We've got provenance, so you can store either XML-based provenance or tag-based provenance about your data, so you can search it and find it. Metadata, that was metadata, wasn't it? And provenance, where everything that happens in the system is all captured and recorded in the log. And so you can go, whenever you look at some data, you can see exactly how it was generated, what analysis we used to produce it, and also what anybody has actually done with that data to analyze it. So we built this system, and this is the version that people get if they log on and use it through the web. So we try to capture a Web 2 type interface for it. So that's the opening page, and this is our workflow editor. So you can drag services that you might have created yourself from the panel on the left, build workflows, and then you can see there's a run button in the middle. If you click run, then that goes off and runs either on our own service, or on a cloud. So I'll talk about how that bit of running it on a cloud works. If you're a human and you run this, when you finish your workflow, you can see the results there. But the way in which we used it for this particular problem, the discovery bus, was that we also have an API, so people can write applications. So everything you can do as a human by clicking, you can do through an API. So you can upload data, you can run workflows, you can retrieve the results and view them. And so we've got quite a few different sorts of applications now which package up particular sort of scientific analyses through these applications which just sit and talk through this API to the rest of the system. For example, we've got some for mobile phones, which are just very simple. So you can select some data, you press a button, it uploads it, analyzes it using workflow, and then just shows you a graph on the phone of the analysis of your results. So we kept the discovery bus on Amazon at the top there, and it then talks to eScience Central through this API where it kicks off workflows which implement the functions of the discovery bus to do the analysis of the data. And at the bottom, as the workflows run, then Azure is called to actually do the grunt work of doing the analysis in parallel. And so to split that up into an extra level of detail, at the top left, you've got discovery bus in point 1, which is calling the eScience Central through this API. The scientists, the chemists have devised these workflows, so they get run by the commands through the API. This generates tasks to actually run the services within the workflows, and these are then sent off to Azure. So there's a description of the software that needs to be run. There's links back to the data on which they run, and these go into Azure. I'll talk in a minute about what happens in Azure. They're run in Azure, and then the results are returned back to eScience Central, and then go back to the discovery bus to be put in the databases, and eventually to appear in the QSAR website. So if we look at the part where there's a handoff between eScience Central and Microsoft Azure, so this is what's happening. So eScience Central, when it gets a task in a workflow, it calls the web node. For those of you who know about Azure, there's web roles and worker roles. So it calls a web node, which takes in the tasks, puts them in a queue, and then the trick is to have enough in the queue of sufficient granularity so you can increase the number of workers on the right-hand side, and so you can get scalability. So just standard sorts of parallelism from 30, 40, 50 years. I guess people have been trying to do this. And it returns results through Azure Blob Storage, which then goes back to eScience Central. So it's quite a simple system once you get it into Azure. So the current status, so this is still work in progress. We have this aim of getting the 5 years down to a few weeks, and we're up to a few tens of weeks at the moment. So we're getting there, but We haven't finished yet. We can run on 100 nodes, which we're pleased about with reasonable utilization, but we're still trying to increase that. And the problem is, well, if you have a look at one of these graphs, so we generate these graphs every day or so to work out what's going on, and it just shows you that Amdahl's law still applies even in clouds. And so what happens is the parts that go in parallel work really well, and we get this big high utilization, the purple line at the beginning. But then all of the coordination, the comparison results creates this long tail. So we're now starting to optimize that and move that into Azure as well, so that that's speeded up. So to summarize then, so the discovery bus I've talked about is this chemistry application, but actually it's quite a general sort of pattern. You can imagine lots of different applications where you've got the stuff you want to do when new data arrives or when you've got new model arrives. I was at a conference a few years ago, and Ian Foster gave a good talk, and he talked about this idea of a data cauldron where you throw in rules and you throw in data and you throw in services, and new data and new rules appear. And this is one particular pattern which matches to that. And it's good for clouds because it's got large but bursty requirements. So there would be no point in buying a big cluster for the discovery bus, because what you want to do is when there's more data appears in your data set, you run it, and then you just shut the system down and you wait for more data, and then you run it intensively. And after each run, you put the data in the website so the chemists can actually use it. I do want to stress that clouds don't make it easier to build these complex, scalable, dependable, distributed systems. It's still as hard as ever. And this is why we set off on this task of thinking about, well, can we abstract out some middleware which actually makes that easier? Are there common things which we could just do once and make available? And you see that in commercial cloud deployments. You know, if you look at the sorts of things that Azure is going to have available, the common sorts of middleware in there for business applications, then I think it's good for us to think about what are the common sorts of middleware for science applications. Let's see if we can do those once. We've shown, I think, that Azure is a good scalable solution. We found it relatively easy to port our applications to this and run them on it, even though some of them are Java, some of them are in R, some of them are in Octave. The people who write these rules and these model building tools, they don't all agree on the same software in which to build it. So we've got a set of software as well as .NET software running on Azure at the moment, and that hasn't really been a problem for us. And as I say, the end result is that we hope that over time we'll build up more and more of these results in this open QSAR website, and that's what the chemists will use. So the chemists won't know anything about the cloud, but they'll be able to benefit from the data that's being generated. Okay, thank you.
Lots of time.
Hi, so I have a question regarding the usage patterns of the science central platforms you currently implement. So I'm curious about the usage pattern. So how does a user or a scientist submit the jobs, the computation jobs, to the system? And second, do you enable any dynamic scaling mechanisms in the current system to adapt to the computational requirements of the user jobs?
Yeah. Okay. So those are good questions. So let me go back to here. So this is how the scientists would create the work that they want to run. So on the left-hand side, you've got this palette of services, and you can add your own services to that in a range of languages: .NET, Java, R, Octave, and you then just drag them and create the workflow. And then when you press run, then it's up to us as the people who manage the science central system what happens. And initially, and still for many of the tasks that we actually run, those services when they actually are executed, they just run on our own service. But the thing that we've done with Azure is now we can also run them on a cloud, in this case Azure behind the scenes. So that gives us scalability. But the user doesn't know anything about that. They just click run, and it's up to us how we schedule that. And the same is true if you call these workflows through the API as well. You've got no control over where they run. Remind me of the second part of your question.
So do you enable any dynamic scaling?
Oh yes.
Yeah.
No, we have a person who does that at the moment. So
okay.
It's quite dynamic, but we would like to be able to automate that. We did some work a few years ago on sort of autonomic computing, where you monitor response times and grab more nodes as appropriate, and that's something that we want to do, but we haven't done it so far.
On the computational chemistry side, way back at the beginning, when you're talking about testing different models, are you talking about trying out different force fields, different parameterizations on those force fields from known data? What's going on there?
Okay, so bear in mind I'm not a chemist. So are you a chemist?
Yeah.
Oh dear. Okay. So yeah. So as I understand it, that when you get the data in the database, is what I've seen, you get a quantitative measure of activity for some particular activity, like toxicity, say, and you get from the molecule, you can derive all sorts of properties from it about the shape, the number of atoms, log P, and so on. And what the modeling system does is to take those quantifiable measures of the structure and try to relate them to the activity through these models. So that's actually what QSAR is doing.
Okay.
Yeah, does that make sense?
Mm-hmm.
Okay. One question on the workflow diagram.
Yeah.
What a chemist that doesn't find a block step for a workflow, what does he do?
Okay. So
he can find, he can upload, he can program, he can script, he can what?
yes. So you can. So at the moment we have a development environment. So you can take some code in R, Octave, .NET, Java, probably some other things I've forgotten about, and you package it in a fairly simple way. It basically just talks about how you get the data that's coming into the service and how to get it out of that service. Then you upload it and it appears as one of those blocks on the left-hand side of the diagram, and then you can use it in workflows. Now we're simplifying that at the moment so that it'd be easier for you, just particularly for scripting languages, just to click on a new block and dump in some R, for example, which seems to be very popular these days with the scientists that we work with, and press save, and then that will be how it's created. But at the moment, you do it in a special environment which packages up the software.
How much data is processed on a per workflow basis typically?
The amount of data that actually flows around the system is relatively small. So it's not, I couldn't give you the exact results, but one of the reasons why it works reasonably well at the moment is that the amount of data that we send from eScience Central to Azure is only a small number of tens of K. Now, I think that's one of the interesting things about clouds, about at what point you commit and say, right, I'm just going to use this cloud because I can't afford to move my data around dynamically. But we're not there yet at the moment, but I'm sure that will come, and then we'll have these hard decisions to make.
You mentioned you collect provenance as part of your platform,
Yeah.
and given that you work in such a heterogeneous environment across Amazon and Azure and probably other external services,
Yeah.
do you see provenance collection getting more and more complex?
The provenance we collect at the moment is basically everything anybody does on the system. So when somebody registers with the system, when they make a social networking connection, when they upload some data, when they share it, when they analyze that data, we record the workflows, the results they produce, and all the services that are run within it. I think that, and that's not actually been very difficult to collect. The hard thing is actually adding value from it. So there's a panel you can go to, and you can look for any piece of data, how it was produced and what anybody's done with it. And that's relatively simple, and people seem to like that. They like the way in which you can get some sort of confidence in how this data was produced. And because everything's in this one system that you can go to through the web, you can go back and have a look at the workflow that produced that data and see if you like it, and if you don't, you can change it or replace it with your own workflow. But the thing we're trying to do now is to use techniques like computational intelligence to actually advise the scientists as they go along. So what I'd like to do is, I won't flick through the page, but if you look at there's a blank bit of space on our web page, and that's going to be filled in not with adverts as you get with a traditional commercial website. That will be filled in with things like, well, of the people who you are connected to, most people who are working on this data would actually use this workflow to analyze it. Or, when somebody goes to workflow, you'd then get advice and say, well, these are the people you know who have actually used this workflow, and this is what they've done with it. And then you might just go and have a look, or you might pick up the phone and talk to them. So I think that's the interesting part of provenance. It's actually not collecting it. It's how you can extract as much value from it as possible to help spread best practice through the system.
So actually, how many active users do you have right now, and what is also their experience, kind of their greatest complaint about the current system, the greatest happiness? Because it seems like a great system, but I'm just curious about, since you actually have users using it.
So we've got 40 to 50 users, although of course the discovery bus looks like one user, and actually that's run, I think we're up to 150,000 workflows through the system in the last few months. So that automated user is our main user, but there are 40 to 50 humans as well running the system. The thing that surprised me was that we put an enormous amount of effort into the workflow and uploading services. And when you go to conferences like this, you always get more questions about that than anything else. When we actually put it in front of scientists, the thing that they use most is just the simple social networking to upload data and to share data in a controlled way with their colleagues. And we have a blogging system which is like an ordinary blogging system, but it's under the same security regime of everything else. So you can use it like a lab notebook, or you can share all your entries or just individual entries with your supervisor or with groups of colleagues and so on. And so you see people using that, and then they'll say, oh, I've got this data, I've analysed it, these are the results I got, I think it's this. And then somebody else will comment and say, well, have you tried this workflow on it? And oh, I've tried this, and so on. So actually, at the moment, the basic collaboration tools that we have, because they can take advantage of the fact that in the blogs you can refer to the data, so people can go back and look at the data, and you can see the workflows which produce that data. They've actually been the most popular parts, rather than all the effort we put into actually generating the workflow editor through a browser, which was quite tricky, and the workflow enactment and so on, the connection to the cloud. So I'm hoping there'll be this pipeline that people start by doing that sort of collaboration and sharing, and then they'll gradually move to doing more and more of their real grunt work of the science in the system.
So all that good computer science is always overlooked. Just toil away in the field, and that's great because they don't notice a problem with it. They just go directly to the chemistry Facebook.
That's right. Yes, that's right.
Time for one more question, maybe a yes/no question.
I think the answer is no.
All right, let's thank Paul again. All right, so Sarval Bansal from IIT Delhi will be talking about some more hardcore systems topics now inside the virtualization layer. So,
thank you. Yes, I mean, probably changing gears from our previous talk. So my talk is looking inside the virtualization layer for performance, security, and software fault tolerance. Okay, so as a background to my talk, there's a lot of virtualization software available in the market. And there's a lot of good virtual.
Your microphone, please.
Oh, I'm so sorry. Okay, so didn't make any difference to it. It's just recording, okay. Okay, so there's a lot of good virtualization software available in the market, and there are two things that I would like to point out. Virtualization software is very much mainstream today, and the use of virtualization software is growing over time. And I mean, assuming with all the cloud computing paradigms that we're talking about really become a reality, a significantly large percentage of our software is going to run virtualized. So virtualization layer is really going to be almost as ubiquitous as an operating system is today. And that's interesting for a systems researcher or from a programming language researcher point of view, because it gives you another place where he can kind of test his silly ideas and play with things. And that's part of what I'm going to do in this talk today. Okay, so I will divide virtual machine monitors into three very broad categories depending on how they implement a virtual machine monitor. The first category of virtual machine monitors is the ones which use binary translation. This is a completely software-only approach where you translate the code of the guest applications and the OS before you execute them by giving it the illusion that it's actually running on a real machine. This approach was pioneered by VMware in 1998 when they were founded. And they are perhaps the single biggest virtualization layer that's actually using this kind of an approach. The second category of virtual machine monitors are the ones which use hardware-assisted virtualization. We're using hardware support available in recent processors, both by Intel and AMD. And this is by far the most common way to virtualize workloads. And there are a list of products which are using this kind of an approach. And the third kind of virtualization platforms is what is called para-virtualization, where the idea is that you do not need to export the exact same abstraction as that of a real machine in a virtual machine. Assuming you could patch or modify the guest operating system in some way, you could perhaps get better performance or better consolidation ratios. And this was an idea that was pioneered by Zen in somewhere around 2003. So you'll notice that some of these products are in more than 2 places, and that's because they're implementing both those things. Okay, so while the virtualization software that we have today is pretty good at what they do, there are some missing features and that's what I'm going to talk about today in this talk. One of the things that none of these virtualization software do is optimize code. So there's been a lot of work in the compiler community before virtualization was as mainstream on dynamically optimizing code. Right? There's been papers, lots of papers on dynamic optimizers, and we feel that a virtualization layer is a good place to kind of actually implement those ideas. The 2 big advantages of doing this at the virtualization layer. One, because the virtualization layer is right at the bottom of your entire software stack, it has the view of the entire operating system and its applications as it's optimizing. So any optimization that you implement there is going to have a much wider effect than, let's say, an application level optimizer. And second is simplicity. One of the reasons why a dynamic code optimizer has perhaps not seen widespread adoption is because an optimizer needs to be really aware of all the various abstractions that an operating system is abstracting and make sure that it's not breaking any of them. Well, because a virtual machine monitor is actually implementing a very small and unbreakable abstraction of a real machine, the complexity is much more manageable when you're doing it at the virtualization layer. Okay, the other thing that you can implement in the virtual machine monitor is security. A virtual machine monitor is usually a very small piece of software. For example, the monitor that we are developing is less than 50,000 lines of code. Compare that with a typical OS, which will easily run into millions of lines of code. And so, because of the small surface attack area of a virtualization layer, it's a good place to kind of enforce your virtualization or your security policies. Now, I'm also going to talk about an interesting idea to be able to tolerate some bugs in the software that a virtualization layer runs above it. Okay, what I also call software fault tolerance. Okay, so what are we doing? Well, we're developing a virtualization layer for the x86 platform from ground up. We decided to do it from ground up because we have kind of made many design decisions which are kind of different from what current virtualization platforms do. So well, we run an unmodified OS, so we're not into the para-virtualization space. We can run an unmodified OS. We dynamically optimize code as it runs, and to be able to do that, we use binary translation. So because our objectives are kind of different, we need to use binary translation, and we cannot kind of just use plain hardware-assisted virtualization. Because we are using binary translation, it gives us a very high degree of control over the system, and allows us to specify security policies which are enforceable at instruction level granularity. And I'm going to give you an example of that. We can record and replay an execution as it's occurring. So we can actually record and replay an execution while the guest software is running. It can install an existing OS. So one of the there's a client virtualization has been a nice buzzword for some time, and one of the desirables is that can I actually install a virtualization layer on an existing system which already has an OS installed on it, and this is one of the desirable one of the features of our thing, and it's transparent to the user and try to keep it as simple as possible. Okay, so in picture mode, this is a traditional picture. There's the hardware. Which has memory, disk, network card, serial ports, and other devices. And the OS is the layer which is in charge of all this hardware. And then the OS is exporting certain kind of abstractions on which the application is written to, and it's running applications. This is the virtualized picture with our virtual machine monitor. The virtual machine monitor basically slides beneath the OS. Now it is in charge of all the hardware devices. but we don't want to get into the business of writing device drivers for all the possible devices in the world. So most of the devices are actually just pass-through devices to the OS, because the OS typically would have device drivers for all these devices. But there are certain devices that we do need control over, because we need control over the keyboard, for example. We need control over the console where we are going to display our stuff, and we need control of the disk where the virtual machine monitor itself is going to live. So those are perhaps the only 3 devices that we really need to emulate or need to write device drivers for. Okay, so I'm going to talk about how we are about the binary translation layer that or the binary translator inside a virtualization layer. Basically, the way it works is that as we are executing code, we divide the code into what we call translation blocks. What is a translation block? Well, a translation block is a snippet of code which ends at either a control flow instruction, like a direct or indirect jump, for example, or when a certain threshold of instructions, which I call max instructions, has been translated. Okay, so a simple scheme to implement a binary translator is the following. I look at the original code fragment, which is the code fragment from either the guest operating system or an application that is running on top of it. I binary translate it and produce the translated code fragment, and then I execute a translated code fragment, and when I get to the end of the translated code fragment, I know what the next instruction pointer is, and I kind of repeat this process. What's the problem with this? Well, the original code fragment is going to be typically less than 10 instructions, and the binary translator is going to be, let's say, around 50,000 instructions on average to it, and you have a straight away 5,000x slowdown. So if I were to actually use this on a real operating system, it won't boot across beyond the first 100 instructions. Not a good idea. An obvious refinement, let me use a cache, right? So the same picture, but now when I translate the code, I actually save it to a cache, which I call the translation cache. The translation cache is being looked up using the address of the code in the original code fragment, which is denoted by the variable x here. And this x, because I'm running below the operating system, is basically the physical address in the system, right? So we are working in the physical address space now. Well, after every translated code fragment, I first look up the translation cache to see if I have already translated a code fragment earlier, and if it's found, well and good. I can just execute it right from the cache. If not, I take the bigger step. This is a good improvement. If my binary translator was 50,000 instructions, my lookup procedure is a hash table lookup, which could be a 5,000 instructions. But still, it's not good, because a 5,000 instruction overhead for every 10 instructions of the translated code fragment is a 500x slowdown. Okay, so we need a better idea. We need the next idea. And the next idea is direct jump chaining. We basically say that in the original code, there's likely to be a lot of direct jumps. And so I could use that information to build in direct jumps in the translated code. So in this control flow graph, let's say there were 4 translation blocks, A, B, C, and D, which are linked using direct jumps, shown as in these arrows. In the translated world, it would look something like this, where after every execution of a translation block, I would need to do a lookup procedure, right, without our direct jump chaining. Well, what I could do is simply link up all these translated block fragments to each other, exactly as they were linked in the original code, and I would have a better performance. At this point, assuming that I would only have direct jumps, my performance of my translated code is very close to native performance, because what I'm really doing is executing the translated code, which is likely to be almost the same size as the original code, and then directly jumping to my destinations, which is very good. There are some subtleties, though, that you need to be careful about, because here I'm talking about a cache environment, right? So in a cache, it's possible for things to get evicted or thrown out. So what happens if one of these translation blocks grown out? There are dangling pointers, and I need to be careful about removing all these dangling pointers. So for example, in this case, if there's a jump to B from A, it will be looked up again, and so you need to be careful about something like this. Okay, so that was direct jumps. Similar issues exist with indirect jumps. And the most common form of indirect jump in code, especially for the x86 architecture, is the function return instruction, right? So a simple thing, let's say this is the control flow of the original code. The translation block A calls the function F, function returns and calls B. Here, at this point, the call instruction is a direct jump, right? So it basically, we can do the same direct jump optimization that I explained to you in the last slide. But at this point, I do not know at translation time what the return address is going to be, right? Somebody could have changed the return address. So what I need to do is I actually need to pop up the return address and look up the return address in my translation cache before I can actually jump to it. Assuming my return happens every 100 instructions in my code, lookup takes 5,000 instructions, there's a 50x slowdown there, which is not good, right? So an optimization, let me have some kind of a cache for the lookup function. Let me have a faster lookup table, which I call the jump table, which is basically an array which can be indexed using a 10 highly optimized 10 instruction assembly code, let's say. This is much better because now if I have a return instruction every 100 instructions and the overhead on average is 10 instructions for every 100 instructions, I only have a 10% overhead. Okay, so those are some of the ideas that we have implemented in our binary translator. I'm going to move straight away to some of the results with all these optimizations that I just described. So this graph is basically giving us some of the good news, where I'm kind of using some small to medium integer programs. Bub sort is a bubble sort routine. Empty loop is a for loop, which is just doing nothing and computing to a large number. I mean, these are kind of pathological cases that we wanted to study. Fibonacci iter is computing the first few Fibonacci series numbers using an iterative method. Hanoi 1, Hanoi 2, Hanoi 3 are three different algorithms, iterative algorithms to solve the towers of Hanoi problem. And printf is a routine which is printing random strings to the console repeatedly. Okay, the bars are basically showing what are the overheads of a binary translator. The blue bars are the default behavior with all the optimizations implemented, and the red bars are the behavior when there was no jump table, and I didn't use a jump table. So let me just focus on the blue bars for a moment. I see that my overheads are actually pretty small, which is the good news, with the maximum overhead being around 13%. And in fact, in some of the cases, I'm finding speedups. So there are very interesting things that are going on here. Because I'm using a binary translator, the cache is smaller than the actual code, and so there are issues with the instruction cache that are actually helping us in some of the cases. It's something quite interesting. Another interesting thing is happening in this benchmark called printf. Because I'm writing to console, and console is one of the emulated devices, what happens is in a native execution, the console I/O port would be written to over and over again, whereas in an emulated case, a lot of those writes get buffered and written to once, giving us an improvement, actually a speed up over the native execution. Okay, so those are the good news. There's some bad news. If there are lots and lots of function returns, there's lots and lots of function calls and returns, the binary translator is actually doomed. Okay, so here are some examples of benchmarks. So Euclid, Fiborek, and Eratosthenes. Euclid is computing the greatest common divisor of two random numbers over and over again of different numbers. Fiborek is basically computing the Fibonacci series again, but this time recursively. So you can imagine that there are lots and lots of function calls and returns. And Eratosthenes is a well-known prime finding the first n prime numbers using the sieve method. Once again, the blue bars are the default behavior, and the red bars are the no jump table behavior. The overheads are much higher, right? 156%, 114%, and these are the overheads. And the reason here is, of course, that there are lots of function returns, and function returns are not well optimized for a binary translator. The reason function returns are so costly are because we are trying to emulate a function return in exactly in semantics, and we could kind of relax that requirement to get better performance. So this is a cause for concern, and we need to kind of solve it going ahead to be able to have really an optimizing VMM, so to say. Okay, this graph shows the advantages of doing chaining versus doing not chaining. I'm going to skip this graph. Okay. This slide shows the effect of the size of the translation block. So recall that my translation block was chosen either at the end of a control flow instruction or when maximum instructions reached, right? So on the x-axis, I basically plot the value of the max instructions parameter starting from 1 through 24. On the y-axis, I'm again plotting the overhead. So you can see that the overhead is very high when each of my translation block is only one instruction large. But very soon, the overhead becomes close to what the best overhead could be. And around 9 instructions, it basically saturates the best value, which plays well with the well-known wisdom that a typical basic block is usually 6 to 8 instructions long. So default value of our translation block is 12 instructions. Okay, this graph basically shows the effect of the translation cache size. So once again, the translation cache is kind of a parameter that can change the performance of your. Because most of the benchmarks that we used were small, the trends are actually pretty much clear. One of the benchmarks that I'd like to bring your attention to is the printf benchmark. Printf has a lot of code, for example, to do the format string parsing and the device driver for the console and stuff like that. And you can see that as the translation cache is increasing, the overhead is decreasing. The two curves are for the two different cache replacement algorithms, namely clock and random. And clock is slightly better than random, let's say. Okay. So what are the optimizations we are implementing? So we're implementing peephole optimizations where we replace a sequence of instructions with a faster sequence of instructions. The nice thing about our binary translator design is that the input peephole translation table is kind of an input to the translator, and we can kind of keep pumping in more peephole translations, which could be either coded in manually or automatically generated. Trace optimizations, where we can kind of look at what's the hottest trace in the code execution and emit special code for that hottest trace. And then cross-layer optimizations that actually transcend OS boundaries, like the system call boundaries, right? Which are not actually possible with either application level dynamic optimizers, and definitely not possible with static translators. So all this is actually well-known stuff, just that we are trying to do it at the virtualization layer. Okay, here's an example very quickly of a peephole translation rule. It says that if there are two loads from the same memory location to two different registers, let me replace it by a load and a move. This is all very well when we are talking about an application level binary translator, but when we are talking about virtualization, when you're talking about the virtualization layer, when you're running an OS on top of us, we need to be a little more careful. For example, what happens for an interrupt? What happens if an interrupt occurs between these two instructions? Right? The interrupt handler could have made certain assumptions on how the code was written. For example, it could have made the assumption that R1 would have M before R0 or whatever, and we don't want to break things in any way, and we cannot make any assumptions about what the interrupt handler could do. The simple solution to handle this is when I receive an interrupt, it could be a timer interrupt, disk interrupt, any other device interrupt, I just delay the delivery of the interrupt to the guest to the end of the current translation. Similarly, exceptions. What happens if there was an exception somewhere in the middle of a translation? Let's say there's an instruction which gets translated into a sequence of instructions, and somewhere here, after I have updated a certain state, there's a page fault. Right? Now the page fault handler could have made, let's say, an assumption over what the stack pointer's value could be. And to be able to do this properly, I need to have some sort of a rollback code. So these are just some subtleties one needs to be careful about when you're doing a binary translator at the virtualization layer. Okay, so I'll change. So the advantage of doing a binary translator is, the primary advantage I feel doing a binary translator is that there's a lot of flexibility and a lot of control over what you could do. So here's an example of how you could, how simple it would be to kind of implement a security policy. So let's say I want to implement a security policy which prevents all stack overflow, buffer overflow attacks. Well, a simple thing to do would be to have a shadow stack in your virtualization layer and say that apart from all the other code that I'm generating for the call instruction, let me emit another instruction in my binary translator which basically pushes the return address to the shadow stack. And the return instruction now, apart from doing all the other stuff that it was doing, also does the following, which means it pops the shadow stack and checks it against the real stack's value to see if they agree or not. Right? So a simple way to kind of implement a security policy which is transparent to everything else. Okay, a similar thing you could do, similarly, because you're doing a binary translator, implementing something like a record and replay is very simple. All I need to do is capture all the non-determinism in the guest. Now, non-determinism is due to either I/O or interrupts, and I can kind of write these rules very easily to log all these events whenever they happen in a binary translator. Okay, so here's a table of how much slowdown it takes to implement a record replay mechanism. Well, these numbers are not very flattering. I'm showing a 200x to 500x slowdown in compute-intensive applications and a 7x slowdown in an I/O-intensive application. But this is mainly because when I'm kind of logging an interrupt, I need to log exactly what is the number, what is the instruction boundary at which I got this interrupt. And to be able to keep this count of instructions, I need to have an instruction per instruction to kind of increment how many instructions I've executed. There's smarter ways to do this. For example, I could use hardware performance counter, and this is something we are working on. But just to give you a flavor of what it takes to do a record replay. In conclusion, we think the virtualization layer is a good place to do many interesting things, and we're excited by this opportunity. The question we are asking is, can we make the virtual machine appear? Well, a virtual machine actually looks completely like a real machine, but can it appear faster than a real machine, and in what situations? More secure and more reliable. Okay, thank you.
We have more time for questions.
I wasn't sure when you were delaying the interrupt. You delayed it on your example by one instruction, but that seemed to be because you had this idea that that was a safe point after one instruction. But how do you know how long you have to delay an interrupt to get to the next safe point?
Okay, so that's basically at the translation boundary, right? So if I receive an interrupt, I kind of see where did I receive the interrupt, and I have some kind of a data structure which says that this original translation is this original source code corresponds to this translated code. And so I have these boundary points at which it's safe to take interrupts, and anywhere in the middle, it's not safe to take interrupts. And I can kind of maintain this data structure, and that's what we do.
The optimizations you do are normally the same across different underlying operating systems and underlying platforms?
Right. So the nice thing is that we are not sitting on top of an operating system. We are sitting below the operating system. Right? So all my experiments here are basically based on an undergraduate operating system called Pintos. But what we want to do eventually is to be able to run a full operating system like either Windows or Linux and be able to kind of see what effects we'd have. We are not dependent on operating system only because we're kind of running directly over hardware and kind of passing through all the devices directly.
But do you think you need to do different kinds of optimizations depending on the underlying platform?
Will I need to do different types of optimizations? Well, yes. I mean, the only answer the best answer would be only after I do the experiments. Okay, thank you. Oh, sorry.
Any other questions? Right. Thank you very much.